So next step is to go into a more technical topic, and that is software engineering. It may not, look so relevant at first, but it really has some aspects that are well relevant to consider. So the important thing is that if you're doing this mass production, working in teams, you're developing your code. Mostly as a student, you're not so interested in developing nice code. You want to have your results. I know it from myself. Mostly you want to solve the problem and fine. But if you are thinking one step further, that maybe you have to do this once more because the referees didn't like your work, or your colleague needs it, or you do another experiment, then it starts making sense to structure your way of coding. And to make it more stable and make sure that you have what you want, there are different concepts that I'm going to talk about now. And the first one is unit testing. Then we should work with repositories, and the full advanced consequence is to work with something called continuous integration. And next slide comes there. So in computer programming, you write your code, but you never know really if it does what it's supposed to. And that's why in computer and software engineering, the concept of unit testing has been developed. And that is about writing a code that tests your code. And with that, you can always do some development and check, does it do what it's supposed to? And probably you actually do it in some way already, because before you let it run on your full data, you usually have a little test case that you test that it's really doing what it's supposed to. And you can do unit testing in every programming language. And the idea is that the units should be small and intuitive to test. So not testing the whole program, big bang. That is not the idea of unit testing, but you take out small pieces. Simple case that you have a function that computes the square root of something, or computing the Euclidean distance of something. Then you run a unit test to check that it actually computes this value. And that is the idea. And this is a very nice paper describing the consequences of not having your code tested. Was published in Nature, or I think it was Nature. And in different languages, Java, C++, MATLAB, R, Python, you have even integrated support for automated testing and reporting. So there is a complete framework that goes through all your tests and reports afterwards, this line didn't work. And then it gives you a hint, okay, then you can start your debugging starting from that. So it actually helps you. Very many reject to write them and try to avoid it as long as possible, but it actually helps. Unfortunately, I didn't start to develop my own code using unit tests, and now I have to do everything in as after work. And the idea of a unit test is, first of all, you have to define what to test. You can, first of all, you should test each part individually. And if you have done it well, you can actually test, you can change things and not being depending on other parts. And that makes the upgrading and expanding of your tools much easier. If you can say that if you change something over here, you got a great idea for an algorithm, then it could happen that over here in your code, something breaks because it doesn't deliver, this part doesn't deliver the information that one needs anymore. And that you quickly can see if you have a nice setup of unit tests. And of course, then you can also test the whole workflow, of course. And that can also then test if you have these problems of remote parts of the code doesn't work. And then it's a question how to test. One way to test is the happy path. So that means check what it's supposed to do. That's the nice and easy one. But you can also, and that's actually the more important part, provoke your code, sending in wrong values and see how it behaves. And then the code is actually supposed to fail, and you should report back how it fails. And to do the testing, it's best to have you need some test data mostly, and that should be as realistic as possible. But you need, as when you do the testing or the training in machine learning, you need to have a ground truth as well. So you have to have the both sides of the data. So it could be some simulated test data. Of course, the unit testing is only as good as you write the code. So if you don't write good tests, then it doesn't cover the cases that may need to be covered. So looking at some examples, we could have this count voxels in image function, and we write different tests. That could be assert count vox on a matrix 0, 3, 3 should be equal to 0. That's good. Then we could say for the 3D case also, so that was for the 2D case. We can also do it for the 3D case. Then we look at a 3 by 3 by 3 volume, and all are zeros. So of course, that also delivers a 0. Then testing that we have the case of diagonal 2D, then we provide the I matrix that is once along the diagonal, and the count voxels should provide 3, otherwise the test fails. The syntax for the unit testing varies between the different unit testing packages. This is one syntax that is used. And then we have our shape analysis. Oh, I forgot to create this one. Let's see if it actually works. Yeah, it does. Good. So here we have different an algorithm for doing shape analysis. It includes first we bring it in the image, we do some component labeling, and then we analyze the objects that were produced. And the analysis is count voxels, is calculate the center volume, and some more features around these objects. And the unit testing should actually target this one and these individually. And in the end, you could also do a big test of everything. But the most important ones are the component labeling and all the metrics that you want to compute. In Python, there is a package called PyTest, and it's well suited for larger projects. So you really write your testing code, and then you can make a set of tests for each module if you have sub-functions with the Python code. And this one could run every time the project is updated. So when you, for example, I come to that later, send it to your repository, then it's automatically tested and run through that. So that would be a way to do it in Python. An example is also here. We have scikit-image, also has these unit tests, and if you follow these links, you would probably get to the tests themselves. But what we do in the test watershed is we have a unit test case. We do something called an 8 here. So that's first an 3x3 matrix, which is Boolean. And then we do test watershed 0, 1, and then we create an algorithm, a data set that should be tested. And now I think I really need to leave that mode to show you. Yeah. Oh, that's very small, sorry. So this is better. So here we created an array of an object. We have a marker array, and then we run the watershed, and then afterwards we should expect an output image like this. And afterwards we look at the error, which is the difference between expected and output. And if error is less than some epsilon, then it's true, and then it's okay. Otherwise, the test will fail and report that, okay, VS01 failed. So this is the thing that you can set up in a unit test. So as you can see, sometimes you write much more testing code than the code of the algorithm itself to make sure that you really have what you want. Still, it's very helpful to test all critical cases. And another way of doing the tests is to do it with the help of so-called doc tests. So then behind every Python function, you can write documentation in something called a doc string. So you do 3 apostrophes in the beginning and 3 apostrophes in the end. And here you can describe what the function is doing. That's actually also good policy to describe what your functions are doing, so you can know it next time without looking in the code. And at some point here, you have an example, and here is how to use the function. And this is actually our test code. This can be used as our test code. And here you create an image, and then we apply a hysteresis threshold with some levels, and this is what we expect as output. And then we have the thresholding code on here, and that can be executed as a testing. And when we do unit testing in Jupyter, then we can first we need to define a little auto test function that does something on the doc string, analyzes doc string to find where the test code is. And when we want to run this test, so for example here, we use the @ auto test. So it tells us this one should run through auto test in order to function, to be tested. The function itself is just add 5, so it's a very simple function. And here we have our little test code that would be those 2 lines. So add 5 with a 5 should give a 10. Otherwise, it's not good. And if we want to do it, testing it on an image processing algorithm, let's move up a little bit more. Here we want to test the label function. And again, we have this auto test part, and we call it simple label. And the main part of the doc string is actually that we create an image, the eye, and then we have our test image that looks like this, that is already tested. Then we do simple label, and when it calls this one, it should actually create a single label in the data. Now, if we would break the original data in 2, so we have one piece up here and one piece up down here, and run the simple label, we would expect there are two items labeled 1 and 2. And if that is running and it works, then it's fine. So then we can just see here, it's everything running as expected. But now if I would instead modify this a bit, for example, I would have something on, there it is. IMG. Let's put it on 0,0. Oops. Equal to 1. And I run this. Then it says, no, I need to define that one. Sorry. So now I actually messed up with the data, and it should. Didn't do as I expected it to. No, wrong. So that one was the one I wanted to. So now it should fail. Yeah. Then it says, okay, this one failed. It expected this array, but got that array. And this gives us an indication. It tells us on line 18, something happened. And then I come back in here and see, okay, this is where the test was. That is the case I need to put more attention to. So again, fix it, and then everything is nice. You can also do unit testing in MATLAB. So then you just have to follow this link. To be honest, I haven't checked this link this year. So maybe it has updated in the MATLAB documentation, but there should be a unit testing framework in MATLAB. So now that we know about unit tests, we can go to the next step, which is test-driven programming. And that is the idea that you define your tests before you even write the functional code. That means you always have some reference to know, does it behave as I want it to while you're developing code. This is usually not the scientific approach to work this way, but in software engineering projects, this is the way that is recommended to work along. And in principle, what these tests are is a coded version of the requirements of the code. And then you can see also how far you have progressed in your development by just running the tests. If test 1 is fixed, then you are at 10%. If test 5 is fixed, then you are at 50%, etc. So that gives also you a progress indicator. And then you can also tell that more information about what you are doing. You can put on requirements that, for example, we have, if you have a sphere, you should have anisotropy 0. If you go for shape analysis and compute the center of volume, you should be within 0.5 pixels accurate in the volume position. That's more a functional requirement. That's if you have 1,000 by 1,000 pixel images, it must be run within 30 seconds. This is kind of an interesting requirement because it depends on which computer you're running on. So if you run it on your laptop, it may take 1 minute, but if you run it on the workstation that it's supposed to, then it may run in 10 seconds instead. So that is very much depending on the hardware. But so you need to specify on which system it needs to run this way. But it's also an interesting criterion because if you have a lot of data to process, then you can actually also then have an estimate how long will your processing run, or can you afford to run at a certain processing speed. It becomes more and more important with the growing amount of data that you have. Repositories is something that is very useful. That's you could call it a database where you store your code. And what it does is, if you work as a single developer, of course, then you can just have see the history of your code, and that gives you a backup functionality. But when you're working in team, then you may be working on different versions of the code. And the task of a repository is then to synchronize what people bring in. And ideally, you should work with branches. I come to that a little bit later. But that is when you implement something new, you don't implement it directly on the hard code, but you take out the code on the side and work on it there. And also the repository is located on the centralized server. So that also has the advantage that if your computer breaks and you have just checked in your code, then you're safe. So it's not a problem that you will lose your code when you lose your computer. So the advantages is, of course, it's easy to go back to earlier versions if you realized, okay, this one I really messed up. It doesn't do what I wanted anymore, and I don't know how to do it. Then you can just go back in what you checked in and see, okay, this is the place where I changed it. It's also good for reproducibility. So it's easier to know what you did at a certain time when you process your data. So if someone asks for, when you send your paper to a review, and in parallel you continue developing, and then the reviewer asks, so what did happen here? Then you have the opportunity to go back and check with that code and even maybe compare to what your new code is doing. And of course, it's easier for a team to work together on the same code without disturbing each other, because that can be quite annoying if everybody are working on the same piece of code and something breaks while you are doing something else. There are different repository frameworks, and the popularity has switched over the years. So that there are, for example, Git. The most well-known one is GitHub, which is open source repository with commercial features. Azure is Microsoft driven repository. Then there are two older ones that I would say early 2000s, or even back in the 90s, Subversion and CVS. They are less used today. And you can even see it in this curve here, that CVS is actually almost down to 0% on the market. And Git is, with the open source development, is increasing a lot. Microsoft has increased very much over the recent years. Reason is probably because of the big market share that Microsoft has, and that it's part of the integration in their development system. And I'm personally using the Git, and there are many servers available out there. And what they do is, the two big ones is GitHub and GitLab. And then there are a couple of others, but and then you can also, of course, set up your own Git server if you like on your system. But usually this is nothing you want to do yourself. This is setting up the server that is provided. And what they provide is mostly a repository itself. You can have issue tracking. That's a way to keep track of bugs or features you want to add. And Then there is also a possibility to do project management, where you more or less take all these issues and put them in a table, and you can say, so you can see the status of your development. So one is called Kanban, which has essentially 3 columns. One is tasks to do, tasks in progress, and tasks completed. So it gives you an overview of how to work. And then a typical repository workflow is that you create a lot of branches. So every issue that you do, you create a branch that is dedicated to that issue. And then once it's done, you make maybe a review even, and then you bring it back into the main branch. And it can look something like this. If you look at it graphically, this is from one of my repositories, just a snapshot, I think from last year or something, where I extracted some branches and do some development, and then I went back. And usually I also name the branches after the different issues. This makes it possible to work on different ideas in parallel without breaking your main code. So the main code should always be compilable and run safely. In the branch, it can be quite a mess. That's up to you what you are coding right now. But afterwards, you should be well structured before you can bring it back into the main topic. That one, I think, was a note that appeared as a slide, so that we skip. Next step is, now that you have both unit tests and repository, you can work with something called continuous integration. And that is a system that senses, oh, there is a new commit on the repository. Let's compile it and run the tests. And that can be done automatically. And down here you can see, oops, that was too much. So here is a view of one of these continuous integration tools. It's called Travis. There are other ones, one called Jenkins, and then a couple of commercial ones. Travis is also semi-free, so you can run a certain number of tests per month, I think. And the outcome is that, first of all, it tells it compiled and the tests run. And at some point it says, that didn't work. And the advantage is, in larger projects, you may want to compile on different operating systems and make sure that each operating system works. And then you get a nice list that this one works on Windows, it works on Linux, but not on the Mac. Gives you actually the message direct, and then you know on which operating system you need to fix things. This may not be the typical thing that you work for many operating systems in a scientific project, but when you come into software engineering, this is not uncommon that you're doing it. So, and that was the end of today's lecture. I'm a little bit early. So what we have talked about is working with multiple modalities, how you can get data from different sources and combine them. And the last part was now about software engineering, how to actually handle your code in order to be more structured and be sure that it's actually doing what it's supposed to. And that was the end of today's lecture. Next week is even more computing. Then it is, I'm going to talk about cluster computing and how to parallelize your code if you have a lot of analysis to do, and how to speed up things to be more efficient.